All right, should be recording now. Okay. So looking through this, yeah, I guess we can just, so I'll start with the acid-base stuff because I know this is like the biggest thing. And it's also like the oldest topic, right? That's probably all the way at the beginning of the quarter. Um, so the one thing that I kind of disagree with in this class is the way that this is taught. You're kind of given a chart, and you're, kind of left to your own devices. The chart is kind of a blessing and a curse because if you don't understand how the chart, I mean, the chart is great. If you know how to work it, you will, you'll have an easy time with this. But if you don't, it's a little tricky. So whenever it comes to the acid-base questions, the number one thing that I always do is just kind of identify in the starting molecule or the starting like formula, like what is the acid and the base. So who is taking the electrons and who is giving them. Usually you just look for, like, if you're looking for a base, you just look for a lone pair, right? Or, I'll put here XS, that just means excess. So like usually an excess, I guess what I should say is like a minus charge, right? You can look for like a minus charge. That's not a guarantee, right? That a minus charge will always be there. But if you see one, that's like a base because it has that lone pair. Acids will typically have a hydrogen on them, right? And they'll have like a lack of like a minus charge or something. I'm going to hope that whatever you get on your final, it's very obvious to see like these two, where there's clearly a minus charge. So we know this is our base. Actually, what am I doing? Let's just use the color here, make it easier. So we see the lone pair here, so we know it's a base. And then we see, I mean, this doesn't have a lone pair, but it has a hydrogen. So it's an acid. Cool thing about these equations, if you can figure out if one of these is an acid or a base, the other one has to be the opposite, right? Like maybe this one might be a little bit tricky to figure out what it is, but hey, we see the minus, so we know that's a base. So this clearly has to be the acid. Okay. As with every acid-base equation, all you're doing is you're swapping a proton. So if this guy has the proton in the other side of our equation, this guy won't have it. And obviously with this one's looking for a proton, so that guy's going to get one. Okay. Because this guy lost a proton, and also because we want to conserve charge, right, we should put a minus charge here. So remember conservation of charge. Right? If this side is net negative, then this side should also be net negative. Conservation of charge applies in a lot of different scenarios too. So we'll see in other places where we can use conservation of charge to just make sure we're doing things correctly. Okay. So this is probably the easier part of acid base, right? Is you just, you're taking two things, you're swapping a proton, you're just drawing the products of it. What's a little bit harder is doing the math, because again, if you don't know how to use the chart, it gets a little difficult. So here's the easy way to do this. Because your chart, your pKa chart concerns acids, right? All right, let me write that a little bit better. If there's anything that I write, I mean, I'm very conscious of the fact that I have really bad handwriting, but I've been reading my handwriting for like a million years. So if there's anything I write that you guys can't like discern, please let me know. I'll just rewrite it. Because obviously I can write it because I know what I wanted to write, or I can read it. Sorry. So if you guys can't, please let me know. Okay. Your pK chart concerns acids. So if you want to focus on something on each side, you want to focus on the acid. So in this case, you would want to focus on this guy here, right? And again, if this guy is the acid on this side, then the other guy has to be the acid on the other side. So the acid has to be the other species here. Okay. For these calculations, it's just product minus reactants. So whatever that value is on your chart, that will give you the KEQ, right? That gives you the equilibrium constant. I don't know what I don't have the chart memorized in my brain. I can just give you like roughly what the value would be for this one, but like this one would roughly be like 25 and this would be roughly like 15. So the math would be 15 minus 25, which is...
You're so close. That one is 25, the other one is 16.
Okay. So then let's just change this to 16. So 16 minus 25, so this would be like -9. Okay. So 10 to the -9 would go here. Now, just to help you guys understand what these numbers mean, The equilibrium constant tells you how likely this is to push to the right. A negative number means that it does not want to push to the right, and a positive number means that it very much wants to push to the right. A way that we can reconcile this number is that if we just think conceptually, right, an O minus versus a C minus, O minus is always happier, right? C minus is not very happy. So it makes sense that if there's a C minus on the right side, the equilibrium doesn't really want to go there, right? So I'll put here not stable, but this is stable. Sorry, let me not put that in the words, right? Let me put that up here. Right, this is more stable. So actually, let's put less stable here. Okay, so it makes sense that this value is negative because it really doesn't want to push that way. So let's say you had a problem like this on your, like, let's say this exact one was on your exam and you got a positive number, something's fishy, right? Something's very fishy, something's not working out. Okay, that's like a last like check you could do just to make sure. Cool. All right. Also, I'll post the slides after. So if like there's anything you guys miss, it's okay. I'll have the slides out. I mean, I don't need them. So cool. All right. All right, so then moving on to this one, same idea, right? And again, these are really clear examples. I really like these ones. So I hope you guys get ones like these on your exam, because you can see that this is O minus and this is SH. So, I mean, I can clearly see OH minus is the base. So I feel very confident. I mean, there's that lone pair, right? I feel very, very confident that this guy here is going to be our acid. Okay, that's the guy with our proton. So to just write my equation, I'm just switching protons, right? So this guy gets a proton, turns into water, and this guy loses a proton. And again, conservation of charge, right? If there is a net negative on this side, there should be a net negative on this side. Okay, so that negative is going to go on the sulfur. I'm gonna have to ballpark this again, but again, if this is the acid on this side, then on the other side, this guy has to be the acid. So we're comparing this guy to this guy. I'll have to ballpark this again, but this should be around 9. Actually, I bet he put this as 10 because 10 is a really nice round number, or maybe not because put that as 16, which is not a round number. Okay, 10 is the value that I would know for this one, or 9 or 10. And then water, oh shoot. Okay, if it's either 14 or 15 that he puts for
It's
this one.
also 16. So the
This is
left
16?
side, yeah, the left side is 10 and the right side is 16.
Okay, cool. So 16 minus 10, that's going to give us 6. So this would be 10 to the 6. So once again, we can come back to that idea of, does our KEQ make sense, right? Does it make sense that an O minus wants to turn into an S minus? If you guys remember from acidity rules, right? CNOF, ClBrIPS, right? Generally speaking, acidity follows this line here, right? We want to go to the right and down. So if we're comparing horizontally, we want to move this way, right? If we're comparing vertically, we want to move this way, okay? Oxygen and sulfur have a vertical relationship. So sulfur is better with the lone pair. It is more acidic, it's more stable. So it does make sense that our equilibrium pushes to the right here. Okay. Cool. All right. So these kinds of acid-base problems, I think as long as you have a method, right, things tend to work out. If I were to think of a harder version of this question, a harder version would probably be something like, let's say we got something like this. Okay, a carboxylate and a ammonium. Oh, actually, I don't even know if he put that one on your chart. Let me check. I think could someone send me the chart actually so I can see what he put on it?
It's on the Discord.
Oh, thanks so much. Okay, let's see. So what could he put on here that would be hard? Did he put that on there? Oh, he did. Okay, so he did. He did put it on there. Okay, so this could be like a hard one. Okay, this guy and this guy. So carboxylate and ammonium, You guys will get more familiar with these guys in 8B if you're going to take it. But again, if I'm looking for who's the acid and the base, another quick rule of thumb that you can use is, hey, if this is a minus, right, I'm more likely to think that this is a base form. Okay, so base forms, right, have a minus. Acid forms tend to have a positive. Okay, so again, quick rule of thumb, right? It's not going to be guaranteed that that's always going to happen, right? You're not always going to get a positive, but if I see one, right, I'm very inclined to think that that's an acid. Okay, so if I'm to do the acid base equation, right, these guys are just going to swap protons. So H is going to go onto the oxygen there, and nitrogen is going to lose the hydrogen. Okay. When I think of conservation of charge here, right, this minus charge here gets neutralized because it gets an H plus, so this becomes 0. And nitrogen loses a H plus, so it loses its positive. So this is also going to be 0. So sometimes if we have, two opposing charges on one side, the other side will just be completely neutral, right? But it makes sense because if this is 0, right, this should also be 0. So it's okay that there's no charges on the right side. Everything adds up. Okay. Now it looks like here you're given the values of for the NH4 plus species to be 10, or it could be 5. Okay. So one big thing that I'm noticing people have a hard time with the acidity is completely matching the molecule to something on there. And one thing you'll want to do is not only can nitrogens and oxygens, not only can they differ in that they're nitrogens and oxygens, but also just what carbon they're connected to. Okay, if you look at the examples in the 5 box, for example, right, we have nitrogens that are either connected in some sense to an sp2 carbon, so something like that, or they are themselves sp2. So there's like an example like this one, something like this. Doesn't matter as long as it looks sp2. Okay. So if a nitrogen is somehow sp2 or it's bonded to an sp2 atom, right, it has a particular value on the pKa chart. But again, it's because it's connected to something sp2. If I have a carbon that's sp3 that's connected to the amine, for example, or it's just like a hydrogen, right, which doesn't really carry. I mean, this nitrogen would just be sp3 in general. These nitrogens are going to carry a higher value. These are the ones that are here at 10 on this chart. Okay, so don't just look at the atom, right? Take a second, to also look at what kind of atom it's connected to, because that can make a whole big difference, right? I mean, 5 and 10, I mean, that's a big difference, right? If you use the number incorrectly, it's going to be a little tragic, right? Because that's a huge difference. So always go out of your way to also just check locally, because if I look over here, right, this completely changes the answer if I have, let's say, like this kind of ammonium, so NH3 plus like this, versus NH2 plus like this. Okay, the value that I use for this acid completely changes, right? This one down here, because it's connected to the sp3, right, I would use 9 for this one, right? I would use a 9 for that one. But if I had this one up here that's sp2, right, I would want to use 5. Okay, for particularly this example, we were doing NH4 plus, so we'll go ahead and just use the 9 value. But we can also just see how the math works out when we use the other ones. Okay, cool. So that's 9. So again, if the nitrogen species on this side is what we use, and on the other side, we're going to use the carboxylate species. Oops, didn't mean to do that. And that guy is always going to be at 5. Okay, that guy's going to be at 5. So when I do my math, right, 5 minus 9, that's -4. Okay, this is going to give us a equilibrium constant of -4. Now, this one's a little bit interesting. I did this one on purpose because if you try to use your, any of the, rule of thumbs that we've used previously, like, oh, let's use our acidity rules to see if this works out. Or, I know sometimes they teach you that, no charge is better than any charge. This one kind of breaks the rules. Okay, so it's always good to just see exceptions and have them explained, because then you won't doubt yourself on the exam. Maybe, you could have everything tip top. You could be, completely prepared, but even the exceptions can throw you off. So it's good to have that contact with us right now. So if this shows up tomorrow, I think your guys' exam is, then, won't catch you guys off too bad. Cool. So that's a difficult one, but now we know how to solve it. Let's just do one more. All right, let's see. Let's see if I can put another tricky one on here. Okay. This one's not too tricky. It's just more of, being able to identify, I suppose. Just the different species. Okay, cool. So for this one, again, I'm looking for something that kind of gives away whether something is an acid or a base. On the left side, oh shoot, I guess I did not mean to do that actually, but it's okay, whatever. On the left side here, right, I can see that this has a minus. So I'm very inclined to think that this is a base. So that makes this guy an acid here. Okay. Hopefully Dr. Helix draws out the hydrogen for you guys. If he doesn't, I guess if you had to find it, well, no, I think he'd probably match it. I don't think he would do anything too crazy. So yeah, so let's just hope. Okay, how about this? So I remember there was a question on your quiz. It was something like this. So I guess you could make it a little bit crazier. So let's say that you guys got a molecule that looks something like this, right? Something that looks like, I mean, this looks like a squid, right? It has like no bearing. It almost looks like nothing on here, right? What I would do is try to match some particular structural feature and see if you can match it anywhere on your chart. So for example, I see here a carbonyl where right next door, they're just carbons, right? There's anything particular special going on. So when I look through the chart, if you guys have it up, that would probably help. When I look through the chart, I can see that, in 2 spots, I can see like a carbon double bonded to an oxygen with carbons next door. I see one in the -7 spot. Okay, so I see this guy, and then, so this is the -7 guy. And then I see another guy like this with the hydrogens drawn out. Okay, the hydrogen drawn out and this is around 20. Since we're looking at the acid form of this molecule, it's just a matter of matching it, right? Does it more like this guy or that guy? Clearly looks more like the right one. So we'll go with the right value. Okay, and it also tells you which H we're concerned with, right? We're concerned with the H's that are right next door. Okay, so yeah, there's a bunch of fluff, right? We have these like 6 extra carbons on the side, but again, that's just fluff. That's just there to scare you, right? Really, we just want to focus on what the pKa chart tells us, which is, hey, if we have hydrogens near a carbonyl, we only really care about the hydrogens that are right next door, right? I don't really care about these guys over here. They're not that special. Okay, they're not that exciting. But these guys over here, right, I do care about them. So that's like a little trick you can use if he doesn't draw out the hydrogen. I don't think he would do that, though. I think that would be a little unfair. A little bit of a mean question, too, but just in case. Okay. So we know that it's this hydrogen here that we're concerned with, and this is our base. So let's go ahead and do our, our swapping. So we'll put, let's do this first. So we know this guy gets a hydrogen. This guy loses a hydrogen. Conservation of charge tells us there should be a minus. So we'll put it right next to the carbonyl like that. Okay, because that's the hydrogen we care about. And I mean, that little bit of groundwork we did earlier kind of helps with the numbers, right? Because we know this is the acid form here. And we figured out that was 20 because, I mean, those are the closest to each other. So when I look over here, right, at this guy, I try to match that. I see that at 25. Okay. Again, what's important is that we have a triple bond H, right? A triple bond H there. It's okay that this doesn't have 2 hydrogens on both sides, right? We're just trying to match a similar quality. So if I do the math, we have 25. Oh, let me just get rid of this. We don't need this anymore. We have 25 minus 20. That gives us 5. Okay. Oh, sorry, not pKa, 10. 10 to the 5th, right? That's going to be our equilibrium constant. Okay. This one's a little bit tricky also to use that little, to use a little bit of our logic here, like why the right side might be a bit more better. If you want a good answer for that, it would just be that when we resonate this, it puts the minus on an oxygen. So putting a minus on an oxygen, that's a really good thing, right? Oxygen's a lot better at stabilizing charges than carbon will ever be. Cool. All right. So in terms of equilibrium questions, these are, I like these ones. They're a little bit easier. If you have a method, it really works out. Okay. But there was a question that kept popping up that had sort of a harder version. I think that one's a really good one to go over. So there was a version of the question. I'm just going to zoom in so I have some like white space. Okay. And I think the particular example looks something like this. It's like something like that. It was close to something like this. I think I looked like that. Okay. And so you guys were asked to draw the form that's dominant at pH 6 and then the form that's dominant at pH of like something really high. I think it was like 11 or 12. I'll just put 12. Okay. So given a molecule and you're just asked what is the charge state of the molecule or what is the ionization state of the molecule at those pHs. So for a problem like this, you could go through the whole like, this pH is, acidic, this pH is basic, this group is blah, 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 blah. I think that at your guys' level, this is a bit of a difficult conversation to have. And there's a lot of information to sort of, use and culminate to make an answer. So the method that I would use that kind of simplifies everything is going to be this method here. So as we've learned, right, these groups here can act as acids or bases, right? They can lose a proton or they can gain a proton. For example, if I look at this group right here, right, this alcohol here, this is a alcohol with an sp3 carbon attached to it, right? I can quickly sketch it just down here. And I know that it has sort of two states, right? One state is that it loses a proton to become O-, and another state is that it gains a proton to become OH2+. Okay. Now, for these two acid forms, we can actually look in the chart and find a value for them, right? So for example, if I wanted to find the OH2+, I look at my chart for anywhere there's an OH2+ or OH3+, looks like we have that at -2. So this value here would be -2. Okay. And then for OH, if I look for that, again, OH specifically connected to an sp3 carbon, right? Because there's two values possible, right? There's 10 and there's 16, right? 10 is if my carbon is sp2 right here. And then 16 is if this is an sp3 carbon. Okay, so when I look right here, that's sp3, so I want to use 16 here. Okay, I could then do this for the nitrogen too. So for the nitrogen, I could say, okay, that's a nitrogen here with an sp3 carbon. So I can write the same sort of values. I can say, hey, this guy has an NH- form and also an NH3+ form. And if I look for the acid form, so NH3+, right, again, NH3+ with an sp3 carbon next door, that's going to be, what did he put again? 10 for that one. And then over here, just NH2, so a neutral nitrogen, right? That's sp3. Where is that going to be? That's going to be 38. Okay. We have one last group here. We have the oxygen that is sp2, right? Or sorry, oxygen connected to sp2 carbon. Okay. So this guy just only has two forms, right? It has either OH or O-. Okay. So we can write down all this information. Once you have this information down, now all you have to do is take the pH that you're at and just plot it against these numbers. So for example, if we're at pH of 6, well, for the sp3 alcohol, where does 6 lie, right? 6 is going to be between -2 and 16. So the dominant form of our sp3 alcohol is going to be in the OH form. Okay, so that's where the pH is, right, relative to the pKa. So this is the form that's dominant. Okay, if I look at 6 in comparison to the nitrogens, right, 6 is to the left of 10. So that means that the NH3+ form is the form that's dominant at pH 6. Okay, do the same thing here, right? This guy is just going to be on the left side here, right? 16 is a really, really high number, right? So unless we have a super, super high number, I mean, both of these guys here. Oh, sorry, not 16. Sorry, this is 10. Sorry, that's 10, but it's still to the left there, so it works out. So 16 and 38, I mean, these are really, really high numbers, right? So unless we have a super crazy number over here, we're probably almost never going to be drawing these guys. Okay, cool. But now that I have this information, I can just take my molecule and just apply it. So at pH 6, the sp3 alcohol is still an OH. So I'm going to go ahead and keep this in OH. Okay. At 6, the amine is protonated as the plus form. And then our sp2 alcohol is, at 6 is just going to be the same thing, just like that. Okay, cool. We can then do the same thing with 12, right? And ask ourselves, where's 12, right? Well, hey, 12 is still here, right? 12 is still in between -2 and 16. So 12 is, this is going to stay the same. But for the amine, right, the sp3 amine, 12 is between 10 and 38. So this is going to be our dominant form now. Okay. And also 12 is to the right of 10. So this is going to be a minus form. So you can go ahead and apply that information. So this is going to be O minus because, right, that it's over here. This is going to be NH3 plus, and this is going to be OH. Okay. What's really the basis of this idea is that, you know, 6 and 12, they do feel like we always learn everything in respect to water, right? Where the pH on a pH scale, right? 7 is like the neutral point, and then we have acidic and basic pHs. But remember that pKa is like the neutral point of that particular group, right? So 7 isn't going to always apply, right? Because some groups, right, their ionization's at 16, 38, right, 10. pKs are really, you know, makes things a little trickier than just saying that, oh, 6 is a acidic pKa, sorry, 6 is acidic pH and 12 is a basic, right? Because, oh, sorry, I drew this wrong. That should be that. What was I lost my train of thought. But you know, I lost my train of thought. I forgot what I was saying. But anyways, pKa is a little bit trickier than just saying that a certain pH is acidic and a certain pH is basic. It's all relative to these numbers. It's all relative to these numbers. So you're welcome to use this method if you like. It's not the best method. It's not the worst method either. It's just it's the one that makes it easier for me to organize all the information. I think someone raised their hand. You can talk or you can write in the chat. It's up to you. I just I'll let you guys know right now. I don't. It's not that I don't read the chat. Is that the chat goes by really fast, and I don't have it open in a tab. So if you write a question in the chat, or if you so let's do this. Raise your hand if you write a question in the chat, and then it will signal to me to read the chat. Or you can just talk. That's also fine too. You know, talking is great because then I'm not just talking to myself for however long this is going to be.
So how did you determine -2 and like 16 between the OH2 plus and the negative OH and the O minus?
So
and
okay,
same for the NH.
So let me ask this question. So are you asking how I got the actual value or how I knew to put it there?
I guess both. How would you know that it's -2 between the OH2 plus and the OH?
Yeah. So the actual values, I actually have your chart open, the one that you're going to get on your exam. I just have it open on my phone right now. So that's how I'm getting the exact number. But how I knew to put -2 here, well, this acidic form, right, is going to be associated with the arrow that it's on, right? And this acidic form is associated with this arrow. So I guess if you write it in my particular order, where left side is most acidic and right side is most basic, I guess, then the arrow, the number on the arrow always pertains to whatever's to the left. So that's how I matched it, if that makes sense.
Gotcha. Thank you.
Cool. All right.
Someone asked if you can go over 12 after this problem.
Yeah, that's great. God damn, it's already 5:40. Jesus. I guess time goes really fast when you're having fun, huh? Okay, cool. So I wanted to do another one. I wanted to make up another one, but just for the sake of time, I'm gonna have to move on. But hopefully this kind of summarizes it. You know, really the best thing you can do with these kind of problems is make up your own. Like go in that chart and like put like 10 of those, like no, don't put 10 of them, but put like 3 of these functional groups together in the same molecule and try to, you know, use different pHs, right? Like I can give you a couple, like use 0, use like 5, use 10, and use like 12 or something. Use these 4 values, right? Make up your own molecules with these, you know, throw them all into a molecule to get, like, I don't know, make a ring or something, and then like throw all of them onto here right? It really doesn't matter, right? As long as they're on there, and predict what those states would look like based on the pKa. Okay, cool. All right, but unfortunately, I do have to move on, which kind of sucks. Okay, someone said 12, right? So we'll go down
Yes,
here.
12, and after 12, can you do 13?
Okay. So oh, all right. I remember this one. I remember this one. A lot of people ask me about this one. So when it comes to chair flips or chair conformers, what's really, really important is that you have to get the stereo down. If you get the stereochemistry wrong, you're just gonna get the question wrong in general. Okay. And then it makes it really hard for your graders to like give you guys partial credit, because if your chair isn't even in the correct stereochemistry, you don't even have the correct molecule. So whenever you're asked this question, right, whether it's most stable, least stable, doesn't matter. Always set your stereochemistry first, okay? Because by setting your stereochemistry, then you can do your flips and then think about axial equatorial, okay? So to even begin drawing this, I just set a reference point. It really doesn't matter what you set as long as you're consistent. So for example, I'm just going to choose to make this carbon 1, and then I'm going to count clockwise like that to 3. Okay. If I do that, then this becomes carbon 1. Like I can make that carbon 1 if I wanted to. For anyone who's like crazy, you can make this carbon 1, right? It's totally up to you. I'm just choosing to set it there. That's my reference point. Okay. I will tell you guys this: if on your exam you write your numbers here and write them here, Helix will bless you with as much partial credit if you don't get the right answer, because it makes everyone's life easier if we know what your reference point is, right? Everyone has a different point, right? Don't make us try to figure it out. I'm just going to set this as carbon 1 and then set this as carbon 1. And then if I counted clockwise here, I'm also going to count clockwise here. Okay. So what really helps is, hey, what do my bonds look like? So I would recommend, if any of you guys are having a hard time with what your bonds look like on a cyclohexane, you dedicate some note card space to this. Okay. Every chair, regardless of which way it looks, has a high point. And that high point is always an L. Okay. On the sides of this L are always going to be an upside down L. This is the pattern that just recurs throughout the whole chair. It goes L, upside down L, then L, then upside down L, and then L again. Okay. Now you don't have to memorize this either, also, because you have 2 note cards, right? Just put it on a note card that the bonds look like that, so that you can get this chair at the very least. Okay. When I do a chair flip, right, to visualize this, so I'm doing it correctly, it's always funny. It's like I can draw this chair perfectly, but this one I always draw really weirdly. The way to visualize how a chair flip works, the high tip goes down and the low tip goes up. Let me go put a different color on that. So this low tip goes up. So this is this is what used to be the low tip, and this is what used to be the high tip, right? So again, as long as you set your reference point, you can always figure out where these are. So this would be carbon. If this were carbon 1, this is also carbon 1. So counting clockwise, this will be 2, 3, 2, 3. Okay. Again, highest point is always an L, and then the ones around it are upside down L's, and then it's gonna be L again, and then upside down L. I guess you could also remember that carbon, the lowest tip is the upside down L, but it's easier to just remember L, I guess. Okay. So if you need to, put this on your note card, make your life easier, right? Don't overthink it. One other thing people like to do is they like to assume that wedges equal up bonds and dashes equal down bonds. That's totally fine. As long as you're consistent, you'll always get this correct. So I will continue that assumption. Up bonds are just whatever is like up on that carbon, down is whatever's down. In my opinion, it's just easier to figure out what the vertical bond is, because the horizontal bond just has to be opposite. So if this is pointing up, this has to be down. Maybe I'm not totally sure that's like what that is, but I know this is down, so this has to be up, right? So that's how you can logic your way through the chair. Okay, cool. So I'm going to set this guy first, and we have like 1, 2, and 3. So this was what, 1, 2, and 3. So I'm going to go ahead and just draw in these bonds, right? The bonds here are going to look like this, and then on 3 is going to look like this, right? That's just based on what I had over here. Okay, it looks like we also have something on 4, right? So I'll throw in the bonds on 4. Okay, again, if I go with the wedges up, dashes down idea, the methyl is a wedge, so it's up. So between these 2 bonds here, CH3 is over here, so H is here. On this guy, this is OH is a wedge, so it's up. So versus this bond, right? OH is going to be here. This is going to be H. And then isopropyl looks like it's pointing down. So this bond, isopropyl is here, right? H is here. Okay. I'm just going to go ahead and get rid of the, oh, I guess I drew it together. I'm just going to go ahead and get rid of the H's because you don't really need them. They don't provide any other value, I suppose. So we go ahead and have that. And now the stereo is set. So this ring here is a correct ring. Okay. So when I go to do my chair flip, again, remember that this point here becomes this point here, right? Because it goes down. This is just going to be 1, 2, 3, and 4, right? I'm just going to set things on my ring again, and then just follow my stereochemical rules, right? You know, one thing that really helps is that when you're doing a ring flip, right, your axial and equatorial should switch. Right, so axial turns into equatorial and backwards. So if CH3 is axial here, then it will be equatorial here. Or I mean, you can still use up down if you want to, right? Like this is up and this is up, right? On 3, right, this is up, it's equatorial. So now on 3, this is going to be.
Whoever is unmuted, can you please mute yourself?
I can do it. Who is it? Let's see who it is.
我靠！
It's a Chu Rongzu.
我就想听他说那个
Got it. Cool. You know, sometimes I let the hot mics go through if they're saying something really funny. I guess I couldn't tell in that instance. Cool. All right. So OH is up and it's axial, so it'll be equatorial now, and it's still up. And then isopropyl is down axial, so it'll be equatorial down in this case. Okay, cool. So again, now that we've got our 2 chairs, now we can begin to talk about which chair is more stable, right? We don't want to have that conversation until we've set both chairs. Right? If we haven't set the chairs yet, then we don't know what they look like. So generally speaking, right, we want our bulky group equatorial. So we want our bulky group equatorial for stability. Right? That's what we want. So when I look at my 3 groups, I have a CH3, an OH, and an isopropyl. General rule of thumb is that bromine is smaller than CH3. What does that mean? Because that's just words. What that means then is that CH3 is larger than pretty much everything on the chart, right? Other than iodine. If I quickly again mock up the periodic table here, right? Bromine's all the way down here, so it beats like literally everything here. But CH3 we're saying is now larger than that. So general rule of thumb: if you have a bulky alkyl chain, that's the chain that you want to prioritize on equatorial. Okay. Let's say that I have isopropyl and I have propyl, right? So I'm just going to change this to propyl, right? Because both are 3-carbon chains, right? Who is bulkier? So branching is what makes bulky things. So if you have 2 bulky groups, okay, I can tell that looks bad. I will rewrite that. If I have 2 bulky groups, right? The branchier one, we want equatorial. Okay, and again, this is for stability. So always read the question, right? Make sure that he's asking for more stable. If he isn't, then go with the opposite of this, right? But branchier is going to be equatorial. Okay. If I look at my 2 chairs, right? Again, isopropyl is the branchier of the 2, so I want that guy equatorial. Nice thing though is that on this chair, everything ends up being equatorial. So this one is really, really good, right? This one is really, really bad. So this is our more stable chair.
For determining stability, do you think that there would be a problem where he would have like one of the chair forms have, say, like an OH and like a bromine form being equatorial, and the other one it would be bulky groups, and we'd have to choose which one? Like at what extent do single, like say like there's like a bromine, a chlorine, and an oxygen on one, like at what point does it overpower a bulky group?
This here is the dominant chair for this species.
Okay, so the bulky would still dominate.
Yeah.
Cool
Yeah.
beans. Thank you.
Yeah. I mean, tert butyl is massive. In the chemistry that I work on, groups like tert butyl are what we call ring freezers, because they will literally lock the ring. This ring will not equilibrate at all. It will not flip. It will always look like this ring. Same thing with like if I had this ring and I had this here, right? I mean, this is obviously a really good ring, But at higher levels of chemistry, you can actually look at conformation and tell whether a reaction will occur based on how the terp-butyl will freeze the ring. So at least at the 8A level, if you have a bulky branchy group, that will always take priority, always. If Dr. Helix writes a good question, which he's good at doing that, he will make sure that he won't make you guys like have to really choose, right? Like this, I think this is a fine one to choose on because it's terp-butyl that's massive. Bromine and alcohol are kind of small in comparison to that. I guess what would be harder is if you had to put a CH3 here, right? But still, I mean, again, if we had to choose between prioritizing one of these groups here, right? I always want to prioritize the bulky group first. Okay, bulky group comes first. Okay, cool. That was a really good question. So it really important, right, is always set the stereo first because he did it on the quiz, right? He put a chair and he gave 4 options and he asked for most stable. And one of the chairs was everything equatorial, right? That is a bait answer. That is such a bait answer to put everything equatorial because that's the answer that the people who just memorize that equatorial is more stable are going to circle. Okay, always set the stereo first because I mean, in this example, everything worked out. But imagine you get an example like this one, right? Where the ring has to have 2 things axial, right? Then you have to choose, well, which 2 things do I want axial, which one do I want equatorial? Okay, so set your stereo, then talk about axial, equatorial, and you will get 99% of these questions correct. Okay, cool.
For bulky groups, how come it's not the one on the left again? And why is it like you look at the one on the right that's bulky?
What do you mean look on the one on the right?
Because you looked on like the line with the 3 carbons, you saw that the right one was equatorial, so it was more stable, right?
This one here?
Like I'm looking at the answer right now.
This
answer.
one?
Yes. And like I'm looking at like the line at the end at the carbons at the 1.
This one?
Yeah. So you looked at that one, right? That's the bulkier group.
Oh, okay. So I'll make this more clear. So I modified this from what the actual thing is. I made it propyl because isopropyl and propyl both have the same number of carbons. So the question becomes who's bulkier? The answer is it's always the one that's branching. So you're not actually looking at this guy. You're looking. I guess this was not a good example because both of these end up equatorial. But if one of these had to be axial, one had to be equatorial, you want to prioritize this guy because it's bulky. It's branching. Sorry.
Okay, so since that one is branching, you focus on that one.
Yeah. So like, imagine there is a ring that looked like this, right? Sorry, I don't know why I drew it there. Let me draw it over here. Imagine there is a ring that looked like this, right? Where propyl had to be up. Let's say they're both up, but one had to be axial, one had to be equatorial. This is the preferred ring flip because the bulkier, branchier group is on the equatorial, right? If I had this here, where this is up and this is facing this way, this is worse. This is better though.
Oh, that makes sense. So like the one on the right is more stable because like the branch one is equatorial.
You mean the one on the left? Sorry, you mean this one?
Oh yeah. That's all
Yeah,
right.
yeah.
Okay, got it.
Cool. All right. Nice. Good questions. All right. Cool. So hopefully that helps with 12. Let's see. So it's already 6 o'clock. That's crazy. How do you guys feel about
13.
Newman's? 13?
It was 12 and 13.
13. Okay. Oh, this one's not too bad. So alkenes, always what makes alkenes more stable is more substituents. So what does that mean? So carbon substituents is what I actually meant to say. So this here has hydrogens. So, someone raised their hand. Let's see. For SN and E, can we go over? Yeah, we can talk. We actually, let's do the reactions after this. Let's do that after this. So for this one, we have 2 carbon substituents. I'll just randomly call them R. This one has 3. 3. And then this one has 2. So if I wanted to, I mean, the most stable out of all of these is going to be this guy here, just because it has 3 groups coming out. Actually, another way you can think about it is that this carbon is tertiary and the pi bonds on it. That might actually be easier to think about. than thinking about labeling these. So this one has a pi bond on the tertiary carbon. So more number of tertiary carbons is better. These would be second degree carbons, right? This would be second degree, this would be third degree, and this would be second degree. Oh, I guess this one is the harder one because, yeah, actually, let's not use that rule then because that's not going to work. Okay, let's not do that. Yeah, just count the number of groups coming out of the pi bond. The more number of groups that are, carbon, the better, right? So this has 3 carbon groups, so 3 R groups. This has 2 groups, and this has 2 groups. Now, between these two, that's a very difficult question, actually. Every professor you ask will give you a different answer for particularly this guy and this guy. But the two that you should know the difference between are cis and trans alkenes. Right, so both of these do have 2 R groups, right? So in terms of R groups, that's not really going to help you out. Trans ends up being more stable because the R groups are away from each other, right? These guys are kind of in each other's faces. So if there were like hydrogens on them, they're going to sterically interact, right? It's not going to be too good. On the other hand, these hydrogens are, or whatever group they're on, these are not at all in each other's faces. So as far as possible. Okay, cool. So you can't really ask the question on this one particularly, which one's least stable. I guess you could choose this one because it does look cis. And this one is like, there's a term for this. We call this geminal. If any of you guys are into like horoscope stuff, geminal is the same as like Gemini because the 2 carbon groups are on the same carbon, so they're like twins. So that's a nice way to remember that term. Okay, but these two, it's a bit difficult. I guess if you wanted to, you could always default to cis being the least stable. So if I had to rank these, 1 being the most, and then like 1 being the most stable, 2 and then 3 being the least stable, right? I guess I would do that way. Yeah, cool. All right. Oh, another way to ask this question, like a different terminology you could use is circle the isomer with lowest delta H, so heat of hydrogenation. Back in the old days when grandpas were doing chemistry, one of the ways they quantified how stable an alkene was they hydrogenated it. So you do the simplest reaction is you take this and you do H2, and then they recorded how much heat came out of it. Okay. Systems that are very stable don't give off a lot of heat. Systems that are not very stable give off a lot of heat. So that's like that value has become kind of synonymous. It's not the best value in my opinion, but it's become synonymous with stability. So I guess I'll put it this way: a low heat. God, that's so bad. Okay, a low heat is stability, and a high heat is instability. So that's like another way he could ask the question, right? Is ask who gives off the lowest delta, who has the lowest delta H value, or who gives off the lowest heat in hydrogenation. The answer would still be this one with the lowest, right? Highest would just be whichever one is unstable, right? I guess then that would be this guy here, but he should have a better example, right? For that guy. Cool. All right. So that's all I have to say for that one. Yeah, so let's I'm making the choice here. Let's go look at these guys real quick. Just because it is 6 o'clock.
Some people earlier said they wanted to go over 9. Or I saw
9,
2 people
okay.
in the chat that said
All right, we'll do 9 then. We'll do 9. All right, cool. All right, and then I really do want to get to. I'll make sure we get to at least talk about 18. So even if it hits the 2 hours, I'll make sure that we'll talk about, because that's like probably the hardest material.
Thank you.
Yeah, cool. All right, so 9. This stuff is the bane of my existence, and it's probably the bane of your existence. It's like, it feels like it's such a hard comparison to make. But there are certain things that can help make this easier. Namely, whenever it comes to enantiomers and diastereomers, just use your RS rules. Okay, so for example, B, right? We have 2 stereocenters, and looks like Helix decided to spin one of them. I'm not very good at 3D manipulation. So what I can just do is I can assign RNS and evaluate what that means, you know, between what relationship those two molecules will have. So for example, if I looked at this molecule, I have this center here where I have an oxygen, I have a carbon and a carbon. Oxygen automatically wins, right? It's the heaviest. But between these two carbons, I have to keep looking. This is a CH2 with a carbon. This is a CH2 with the carbon. So these carbons are not really going to help me. I got to move on. I got to move a little bit deeper. So I'll have to go to here and here. This is a H3. So there's 3 H's here. And this is an oxygen, H, and a carbon, right? So I have oxygen, I have H and carbon. So heaviest first difference, right? H versus oxygen, oxygen automatically wins. So this is going to be 2 and this is going to be 3. Okay, so when I draw my line here, right, 1, 2 to 3, this is going to be a clockwise line. Hydrogen is in the back, so I know there's no shenanigans there. So this is going to be R. So that carbon is R. Okay, cool. If I do the same thing on the other side, right? Again, I look at this carbon here, right? I have an oxygen, I have a carbon and a carbon. So oxygen automatically wins 1. I look here and here, I have, looks like a CHH, right? Because I have 2 H's and I have a carbon. And then here I have an H and an H and an H because I just have 3 hydrogens coming out of that. So this guy wins 2, this guy wins 3. Again, hydrogen's in the back, so I know there's no shenanigans there. So 1 to 2 to 3. That looks like to me a clockwise line, so this is also R. Okay, so now that I've set what this molecule is, right? You know, let's think about what would need to be true for either enantiomer or diastereomer. Okay, enantiomers are mirror images, so that means that when I look in the mirror, I should get the exact opposite, right? In stereocenter, right? I should get SS. So if I do the stereochemistry of this molecule and I get SS, I know these are enantiomers. Okay, diastereomers are any other relationship. So enantiomer is specifically the mirror image relationship. So, you know, if something's RR, the other has to be SS, or like, let's say it was like RS and the opposite has to be SR, right? Diastereomer is any other relationship. So one relationship that can, you know, that can be a diastereomer relationship is, let's say I get RR, but on this molecule, I get RS, right? Well, hey, that's not completely inverted, right? That's not SS like I need for the enantiomer. So this is one possible diastereomeric relationship. Another possibility is SR. Okay, SR is another possibility I could get as a diastereomeric relationship. Okay, so if your molecule is not completely inverting, it's good, you know, it's okay to revert to diastereomer. The only time I would be careful is, like, you know, imagine we did this molecule and we got RR. Oh, wait a minute, RR is the same molecule. So these are identical. Okay, cool. So, I mean, this center is literally the same. So this is going to be R also, which tells me this can never be enantiomers. Okay, so enantiomer is already off the table, right? Now it's a matter of, is it diastereomer or is it identical? Okay, I can just do the stereo again. I already did kind of the groundwork, right? I figured out that OH is 1, CH3 was 3, and this is 2. H is in the back, so no shenanigans. 1 to 2 to 3. That to me does not look clockwise. That looks to me as counterclockwise. So this is going to be S. Okay. So if I have an RR molecule and I have an RS molecule, that is a diastereomeric relationship. Okay, that's a diastereomeric relationship. Okay. If this was RR, it would have been identical. And then again, if this was SS, it would have been enantiomeric. Now, one thing you can also do is you could also do a 3D manipulation on this. So if you're able to visualize this, that's great. If not, that's okay. You can, I mean, obviously there's other methods you can use. But one thing you can do is you can try to match the structure by spinning the carbon. Okay. So if I look at this structure here, that's easier to visualize, right? The CH3 is in the plane, right? It's in the plane. So what I can do is I can take this CH3 and I can say, hey, I want to move this CH3 into the plane. Okay. Well, if I do that, then OH has to move into the back, and then this H has to move into the front. Okay, so the wedge group goes to the plane, plane group goes into the back, and then back comes to the front. Notice how I made sure my arrows moved in a singular line, right? It wouldn't be possible for me to move this methyl to the plane, and then this guy goes backwards this way, right? That's opposing the spin. So one way you can make sure you're doing this spin correctly is that when you're drawing your lines, none of your lines oppose each other, right? If I made H come to the plane, I mean, that'd be opposing it, right? So it's got to go forward like that. Okay. If I redraw this, right, this center stays the same. I will keep the dash wedge and the plane the same here as they're represented. Remember, methyl came to the front, so it's here. OH came to the back, and then H came to the front. So this is what this molecule will look like. I can also redraw it. Like if I really want to make it look exactly the same, I can redraw it like this without the hydrogen. Okay. And now I can compare these two molecules. Okay. One little trick you can also use for diastereomers is diastereomers are cis-trans isomers, or I guess easy isomers. You can also say that as well. So they can also be easy isomers. If I look at these two OHs, you can imagine they're in the same plane, right? They're both wedges. So this would be cis, and this OH is a dash, this is a wedge. This would be trans, right? Because their relationship is that, or their difference is cis and trans, they would also be diastereomeric. Okay, so another way that you can also use. So you can use RS, you can use 3D manipulation, and then also once you've done the 3D manipulation, you can also then say, oh, this is cis and this is trans, they've got to be diastereomers. Okay, cool. Now, the one type of molecule that you always have to make out, like, you know, you always have to look out for it, okay, are the mesomolecules. These guys are the sneaky ones, okay? So there's typically two variants of meso. There is the easy to see and there's the hard to see. The easy to see is if you have a molecule like this, right? Where you have two centers that look practically identical. When I draw the mirror plane line, right, I can see that the right side just looks like the left side. These are the easy mesos, okay? One way that you can also tell meso is if one side is R, the other has to be S. So that's a quick check you can do to make sure this molecule has that internal mirror plane. So this is very clearly meso. That's an easy one. Another usual easy one is anytime you have like a ring, right? Cis rings, whether they're 1, 2, 1, 3, or actually 1, 2, and 1, 3 are the ones you want to look out for. So let's say I had an OH here and an OH here. I see that there's a mirror plane here, right? Right side looks like the left side. This is clearly meso. Oh, so someone raised their hand. Aren't they also constitutional isomers? Yeah, so you can think about it this way. This order he has here is actually like, it's sort of like a telescoping order where it's like you make sure they're constitutional and then you move on to enantiomer, diastereomer, or identical. So it's like you're gonna get more and more like specific. You wouldn't just resort to one of these things, or like you wouldn't just like give them multiple labels, right? And also like if you call, actually wait, sorry, I'm confusing this. If you call something a constitutional isomer, you're saying that they have a different structure. So let's just talk about this really quickly. So a great way to tell constitutional isomers is they have different names, right? Like if I tried to name this guy and this guy, they have different names, right? Like this would be like if I were to count the alkene like this, 1, 2, 3, 4, 1, 2, 3, 4. This would be a 5-methyl. Sorry, that's really bad. And then this would be like a 2-methyl, right? They have completely different names. So these would be constitutional because they have different names, but these wouldn't because the base name for these is exactly the same, right? Both of them are 2,4 diols, right? And 1, 2, 3, 4, 5, 6. They'd be 2,4 hexane diols. So the name would be the same there. Okay. Hopefully that clears that up. But like I was saying, oh yeah, so the meso right side looks like the left side. So there are some that are really easy, right? You're going to see them and it's like, wow, that's obviously meso, right? And again, if I did the R and S, this would be R, this would be S. Okay. The hard ones, you can even just write this down, is like this one here. Okay. This molecule here, let me give it a bit of more space. Okay. Now this molecule doesn't have like a very apparent like mirror plane. Oh, sorry, not this, right? But it does have one, and this is a mesomolecule. So there's several different ways you can prove this yourself, okay? One thing you can do is you can do the 3D manipulation again, right? So if I draw in the wedge H, right? I can spin things, right? So I can say wedge H goes to the plane goes to the dash, and then dash goes to the wedge, right? I could do that. And so if I kind of draw everything again, that puts this here. Actually, that's, oh, I guess that won't be really helpful spinning it like that. So you can do a 3D manipulation, but this manipulation is a bit difficult. I can't think of a good way to explain this one. So because I can't think of an easy way to explain this one, I won't use that tactic. Because I mean, if you can see it in your head, you could spin this in a way to make it look meso, but I don't feel comfortable with a method that I can use all the time, or I don't feel comfortable showing you guys a way to do that. So I don't want to confuse anyone. So we won't use that. But one thing you can use is that R and S trick, right? We see two centers with the same thing, so we can draw our supposed line. If this is R and this is S, or like this is S and this is R, this is a mesomolecule. Okay. If I did this center here, this would be 1, this would be 2, this would be 3, right? That to me looks R, right? And then I could do the same thing here, 1 to 2 to 3, right? That also initially looks R, but H is doing some shenanigans, right? H is in the front. So whenever H is a wedge, we just flip our result. So H wedge, flip result. So this R becomes an S. So this is an RS molecule. So this is in fact meso. So this is one way that you can do it, is you can just use the, the most empirical method, right? Just set the centers, and if it follows the meso rule, it's meso. Okay, so we could do that. Another thing you can do that's a bit more visual, but doesn't really involve any flipping, is realizing this particular, there's this one particular thing about mesomolecules. Okay. Not only do they have mirror planes, but if I were to kind of sketch out like all the like groups and their relationships. So what do I mean by that? If I look at the bromines are trans to each other. Okay. So on both these sensors, they have a bromine, those bromines are trans. If I look at the H's are trans. And if I look at the CH3s, the CH3s are trans. Okay. This is the symmetry that we're talking about that we see in meso, when the like groups all have the same stereochemistry, okay, or stereochemical relationship. So BRs are trans, H are trans, and methyls are trans. This is a meso molecule. You can actually apply this to these molecules as well, right? It's just that in this in these cases they're not trans to each other, right? In these cases, if I look at the bromines are cis. The hydrogens are cis, and the methyls are cis. Okay, this is also congruent with the mesomolecule. Okay, you can also do it even here too, on all of these. So you can use this little trick here if it makes sense. And some people have a hard time with this one. I can understand why. It's a very it's a visual thing. These H's are cis. Right, these OHs are cis, and then like the ring, right, is cis to itself. So I mean, rings have to be cis. So these CH2s here are cis. So I'll just say the ring is cis. Okay, I guess a good way to sort of like hammer this in is to look at an example that might be meso and figure out why it's not. Right, like let's say that I have this guy and this guy. Right, I mean, this looks meso. It falls into order with everything we say is meso, but we can use every single rule we just learned to kind of break that. For example, if I did the R and S thing, right, this would be R and this would be R, right? Remember, if I have a mirror plane, one side has to be R, one side has to be S. So just off the RS rule, this already fails. Okay, so that guy's not going to work. Okay, we can use the cis trans rule, right? I can see here that bromine, right? These bromines are both wedges, so bromine is cis. Right, hydrogens are both dashes, so hydrogens are cis, but oh no, the methyls are facing not in the same direction, so this is going to be trans. So this is not meso. Okay, so mesomolecules, I mean, again, you guys need a note card, so I would just go and look at the hardest possible examples. I think really this one's the hardest one, right? Because it doesn't immediately look like that, but go ahead and write those down. right? Don't stress, treat your note card like your second brain, right? You're allowed to store some stuff there as well. Okay. So meso is one of those things that I would put there. Okay, cool. Now, one last thing that I want to cover for this before we move on. Sometimes you'll get molecules. So we'll get this here. So we know this is meso, but sometimes we'll add in like something in the middle here, right? We'll add a center there. Huh? What? Yeah, get whatever. Anything, I don't care. Yeah. Huh? Yeah. Okay. Cool. Sorry, that was my sister. But sometimes we'll add in these like random, stereochemical centers in the middle. They can be a little scary. Don't worry. Here's a little trick. If you ever draw a mirror plane and that line cuts through a center that is quote unquote stereochemical, well, that center is actually not stereochemical at all. The exact definition of chirality is that it has no mirror plane through it. If you draw a line and it goes through a carbon, that carbon can never be chiral because it has a mirror plane. Okay, that's why these carbons here can still be assigned stereochemistry because they appear to be chiral. It's just that their internal mirror plane cancels them out. Anytime you have a line through a carbon, not chiral at all. So I mentioned earlier that we can have 1,2 cis and 1,3 cis meso molecules. So these guys can be meso, but 1,4 will never be meso. Why is that? Because when I draw my mirror plane, it cuts through those 2 carbons that we thought were chiral. And again, chiral carbons cannot have a mirror plane. So if I cut through the carbon, this is neither of these are R or S. I mean, you could even try to assign it. It wouldn't work. So this would be just achiral in general. Okay. Cool. All right. So there we go with that stuff. That's just how I would do it. Oh, so I think someone raised their hand. Let's see.
Oh, sorry, I was just asking for the other question that I sent in the chat earlier.
Sorry, I have to find it. Could you just tell me because there's like
Oh
a
yeah,
lot of
yeah. I was just asking, sorry, after we're done with this, if we could go over the elimination substitution, which molecules would be the fastest for each reaction?
yeah.
Yeah.
Okay.
Okay.
Do that. Let's do that. Cool. All right. All right. So predicting reactions. This is probably like, oh my God, we just learned this all in the last couple of days and now we have to reproduce on the exam. So how does this work? So when it comes to predicting reactions, there's really only 2 things you have to focus on, at least for not the alkene reactions. I think alkene reactions should be fairly okay by now. We can go over B and C very quickly. On the 8th level, they don't make it very difficult. But for example, E, D, and A, right? I mean, we have alkyl halides and we have nucleophiles. Like, what does all this mean? Okay, so what can we do to organize this formation? Well, first, let's just talk a little bit about what the different reactions are, and then we'll look at all the different components. Okay, so in general, we have 2 types of reactions. We have bimolecular reactions, and then we have unimolecular reactions. So I'll just put here by M, and we have our SN2 and we have our E2. So these are our bimoleculars, and then we have our unimoleculars. Okay, so uni-M. This is just SN1, E1. Okay. Our bimolecular reactions are typically done by strong nucleophiles. Okay, so strong nucleophiles, and they're usually, actually, yeah. You know what? No, this approach is a bit confusing. Let's just talk about them one at a time. So we'll start with the bimoleculars. We'll just do SN2. Oh, someone raised their hand. Do you have a question?
Yeah, I have a question on a different problem though.
Oh, okay. Which one?
So for 10, it's
10?
the miso ones, but I was confused by the one on the far right is miso.
Oh,
Because
so
it's 2 methyl groups.
So remember that meso is, so this is a great example of meso, right? Because if I draw my line, I have an R center and an S center on either side, right? That would be a meso. If I try to find some mirror plane where there's like left side looks like right side, I guess, okay, one thing you can realize is that if I kind of flatten the molecule on the isopropyl end, yes, there would be a mirror plane, but would there be an R center and an S center on either side?
No.
No, so that wouldn't be meso. Okay, so what's really important is that meso are molecules that should have been chiral, but they canceled themselves out. Okay, they had an R center and an S center that were identical, so whatever chiral activity they had is just gone. They don't have it anymore. Okay, so this molecule will purely just be chiral because it just has an R center on it. Or is that R? Yeah, it is R.
Oh, I got confused because it's circled on the key. So I was like, huh.
Yeah, so I messed this up with someone else working on this.
Goodness.
It said box.
Sorry.
Yeah, it said box. Yeah.
I'm sorry.
No, it's okay. I made that exact same mistake too when I was working on this with someone. So makes sense. Cool. All right. So let's just talk about I think it's just at your guys' level, I'll just talk about what you need to know for the reaction. And then we'll just kind of reproduce it. So SN2, what is SN2? SN2 is when I have some alkyl halide, which I'll just put X here because it doesn't matter what the halide is. And I throw in a nucleophile. And that nucleophile substitutes the nitrogen, or not the nitrogen, sorry, the X group. So X group is like a halogen or something. Okay. So what are some qualities of this reaction that we need to know? Okay. Well, one really cool thing to know is that if I were to increase the sterics of this reaction, so if I were to do this and then do this, right, the rate of the reaction decreases immensely going towards tertiary. Okay, so this is the rate. And so primary is the fastest, or really methyl is the fastest. So there should be another one here, CH3X, and that will change into the nucleophile. This is by far the fastest, but the slowest is tertiary. And this is so slow, right? Tertiary never encounters SN2 mechanics. Okay, so in terms of what is the fastest, or what is the best substrate for SN2? Primary methyl substrates are the best, hands down, for an SN2 reaction. Okay, so if I'm thinking of what instances I might see in SN2, I'm thinking mainly primary and methyl here. Okay, so these are the fastest. Now, that's not to say that these are the only guys that will do it, or that anytime I see these, I should always think that, but it's something I could think of, right? I can think that these are going to be the fastest substrates. Sorry, someone raised their hand. Let's see.
Yeah, so is it because when the nucleophile attacks, like it's easier to attack when there's less sterics or something in the way? Sorry,
Yeah.
I just don't know why. Yeah, okay.
Yeah, exactly. Yeah, that was just the point I was going to get to, right? The reason why it's faster, right? Because it's like, what is making it faster is, think about it, right? What we're doing when we're going to tertiary is we're increasing the steric bulk, okay? For those of you that are really into like the World Cup right now, imagine if there was like 10 goalies, right? Imagine a team could have 10 goalies on their goalpost. In what world are you scoring a shot, right? You're scoring a shot when there's absolutely no goalies, right? You fake out the goalie from his post, or I don't know how soccer works. I'm just saying things now. But the less things you have blocking you from this attack, right, the easier it is for the nucleophile to intercept. So way easier to attack. Secondary is not too bad. Like it gets, it's not too bad. You just kind of have to make your way in there. It's a little bit slower. But I mean, come on, man. I'm not, nucleophiles are never spending any time trying to navigate this forest of carbons, right? They're lost just as much as we are, right? So never are we going to see SN2 happen on a tertiary center. Okay, so that's a really important thing too, is that because nucleophiles are navigating the bulk behind the leaving group, SN2s are backside mechanisms. Okay, so this is a backside mechanism. So for a majority of substrates like primary and methyls, this doesn't really mean much. But what it does mean is that if I have a secondary substrate, so if I manage to do a secondary substrate and it's chiral, right, I will experience an inversion. So what does inversion mean? So let's say that I have, a chloride here with a wedge, right? And I have a nucleophile, right? Remember, backside attack means I'm going to approach from the opposite side of that leaving group, right? From behind it. So in this case, that's sneaking up behind it on the dash face. So when chlorine is attacked here, right, it's pushed off from the back. So what I will get is a nucleophile with the dash. Okay. If I take the same chloride, but I put the chloride in the back, right, who is the backside relative to the nucleophile? That's going to be my front face. So this is going to make its way from the front, kick off that chlorine, and what I get is a wedge nucleophile. So whenever we're thinking about the 3D plane, right, dashes and wedges, inversion is pretty simple to visualize, right? If I have a wedge leaving group, I'm approaching from the dash face. If I have a dash leaving group, I'm approaching from the wedge face. Where it's a little bit trickier, right, is when I have a leaving group on the flat plane. Okay, I have a leaving group on the flat plane. Okay, if a nucleophile is approaching, again, it is going to approach from the opposite end, but it's approaching from the flat plane. So whatever my groups here are on the dash and the wedge, they're going to stay the same. So dash wedge groups stay exactly the same. So if I call this group 1, group 2, group 1 and 2 stay exactly the same. But what's going to invert is that H is going to go into the back, and the nucleophile is going to come here over, or I guess it's an attack from here. So it's not, I guess it's not going to the back, it's going to the right, and the nucleophile is adding in from the left. Okay, so all of this is just to say, don't just always assume that your dashes and wedges should always be inverting. They should only be inverting if that's the plane you're attacking on. So if your leaving group is a dash or a wedge, right, then you'll expect inversion on that bond, right? You'll expect dash wedge inversion. But if it's on the plane, we're going to get planar inversion, right? Where if the chlorine was on the right side, now the nucleophile is on the left side. Okay. Cool. This is a really specific example. I only mention this because there was a very hard professor that was teaching this class, and they would ask questions from all different perspectives. I don't think you'll have to experience this, but it doesn't hurt for me to just say it and just have it on the screen there. Okay. So cool. All right. So nucleophile is going to backside attack just like that. Okay. Cool. So SN2, we have a strong nucleophile that does a backside attack. And so when we have secondary substrates that are chiral, we will expect there to be a bond inversion, right? But secondary is kind of where we have the cutoff in terms of where SN2 can happen, right? This reaction is incredibly sensitive to sterics, incredibly sensitive. Okay. So just making the jump, honestly, just making the jump from primary to secondary can be on the order of hours, right? Some primary SN2s take literally like 30 minutes, but you make it secondary and it takes almost like 3-4 hours. So that's how much of a difference it makes, to the point where tertiary, I mean, it's not even an SN2 reaction anymore. It's a different reaction. Okay, cool. Now, I'm going to add a little note here about the nucleophile, and we'll come back to this note, because this note's not going to make sense right now, but usually we'll use weakly basic anions. Okay, we'll usually use weakly basic anions for SN2. Why weakly basic won't make sense until we talk about E2. Okay, let's talk about that now. Okay, cool. Again, I am like saving the slides for this, so don't stress too much if I mean, it's just for the sake of time, I just kind of have to go a little fast right now. But you guys can get all the information afterwards too. Cool. So E2, what's going on with E2? Well, let's say I take that substrate, and instead of attacking on that backside carbon, what I do instead is I attack on this next door carbon. Okay. So a little bit of terminology that'll help you guys out. The carbon that holds the leaving group, we call this alpha. And then the next door carbon to alpha, we call beta. Okay. So what does our nucleophile do? What our nucleophile does is it attacks that beta carbon, the hydrogen on it. The electrons shift between alpha and beta, and we kick off the bromine. So what we get is an alpha beta double bond. Okay. This is an elimination. Okay. So one thing to notice from this is we have a pi bond forming. That's a very good indicator. That is a very good indicator of elimination. The other thing is that our nucleophile takes an H, right? It takes an H+. So the best substrates for E2, or sorry, the best nucleophiles for E2 are going to be strongly basic nucleophiles. So this is why I made that point just a second ago on SN2, right? Why is it that SN2 is better with weakly basic? Because strongly basic nucleophiles that like protons are going to want to do E2. Okay, so that's like one of the biggest differences we can make on the nucleophile end of things. Okay. If I were to increase again the bulk, so if I do this here and I were to run these reactions again, I'll just label alpha and beta for the sake of labeling them, right? We will form our products, but unlike, oh, actually, did I do this right? Okay, let me do this. Let me make these a little bit longer. That way you can see a difference. Okay, cool. Unlike SN2 though, the rate of this reaction increases drastically towards the tertiary. So this is the fastest. So when I see secondary and tertiary substrates, you know, I think these guys are really good for E2, right? Again, I'm not saying that primary can't do E2, right? It can do E2 in some cases, but we'll have to have a special case, right? A special case where primary does SN2, or sorry, E2, okay? Now, this is always a bit of a cheeky question, but if I look at my primary substrate here, in terms of E2, there is no E2, sorry, methyl substrate. My methyl substrate has no E2. And this should be fairly answerable, right? We have an alpha and a beta carbon for E2. There's only an alpha carbon on the methyl. So we can never have E2 on a methyl substrate. Okay, so this is virtually zero. But that's okay, it makes sense, right? It's not like this like wacky chemistry going on. It's because there's not even enough carbons to make the pi bond. Okay. So this is E2 on the basic level, right? Of, hey, we have substrates that can be eliminated by basic nucleophiles and they'll make pi bonds, right? And the more more sterically hindered our substrate is, right, the better the reaction is overall, the faster it is, right? The main reason for this is if we go back to pi bond stabilities, or if I look at these pi bonds, remember that one question we're asked for the most stable isomer, we can see here that this has 3 alkyl groups, 1 alkyl group, 0 alkyl groups, right? Increasing, that's so bad, let me rewrite that. Increasing alkyl groups, right, indicates more stable alkene. Okay, and I'll put alk here. Okay, and so having a more stable alkene means that our transition state is easier to access through this reaction. Okay, so that's why it gets faster here. So for those kind of questions, we're to ask like what's faster or what makes a substrate faster? Currently, right, SN2 gets faster with less bulk, and E2 gets faster with more bulk. Okay, so we'll see how SN1, E1 fit in the end, and we'll see if there's like any like trend or any like, you know, quick, easy trick you can memorize for that. Okay, now where E2 gets a little difficult, not too difficult, you just have to remember extra thing, is when we have substrates, like a secondary substrate, where when I label my alpha, I have 2 different betas. Okay, I have 2 different betas. I have a beta 1 and a beta 2, right? One is a CH3, one is a CH2. Whenever I have a less sub beta, right, the reaction on this center, right, is preferred when I use something called a bulky base. So there's 2 of these in this class you need to know. They are LDA, so lithium diisopropylamide, and then tert butoxide. Usually countered with, it could be any counter ion, but the usual is potassium. No real reason why. Okay, so these are our bulky base. So if you see one of these guys, they'll prefer the attack on that less sub beta. Okay, if I want to attack on the more sub beta, I can use virtually any other base. So what we call small bases, usually like ethoxides, methoxides, propoxides, NH2 minuses, right? Anything that's not these 2 guys here, right? The list can go pretty long. Okay, so choosing which side attacks, right, will just be based on whatever base is on your arrow. Okay, now, oh, someone raised their hand.
Oh yeah, I raised my hand because I had a question on how you got the product for the second one. How you got the double bond.
Did I mess it up? Okay, so what I did was this. So if I draw it out, like nicer, then this H, I mean, they're all the same, but this H will go here, this will go here. So what you can do is you can kind of draw the molecule with everything there, and then draw on your pi bond. Obviously, this is not nice. I mean, don't draw this on your exam. This doesn't look very nice, but these two groups should be coming out of the left side. So I'll just redraw this to have that like that. Oh, so I added a carbon. That's what I did wrong. Okay. Or not on that side. It should be this. Wait, no, that should be fine, actually, right? Yeah. Yeah, this is fine.
Oh,
Okay.
I meant the one above that. How do you
This one?
get that product? How did you get that product?
Yeah. So always what you're forming is an alpha beta double bond. So you can just draw the same structure without bromine, and then between alpha and beta, just draw a double bond.
Okay. Were there any arrows?
So I can take this, do that, do that.
Oh, okay. That makes sense.
Okay. Cool. All right. So again, choosing between these two, bulky versus small. Now, here's a cool little tip for you guys. If you ever have a, oh, it looks like two people raised their hand. So someone's got to figure out who's going first. It's not gonna be me.
Oh, sorry, could you explain again why more bulk makes it faster? I didn't understand that well, sorry.
Yeah, so the reason why that is remember, alkenes that are more substituted are more stable, right? So when we're going through the transition state, so let's say we're going through the transition state for this E2, right? The partial pi bond that forms is more stable the more substituted groups you have. So that transition state hump is lower. So it's easier to access this pi bond. So like this is a base taking this proton. This portion here is stabilized by as the more R groups you have around it. So actually, really, I should put R here. Right. So the fact that there's 3 groups here, that stabilizes that transition state. On the other hand, let's say that I had this transition state here. Right. This transition state is not as stable because you only have one group that can stabilize. So this group would stabilize, but all 3 of these groups would stabilize right here.
Oh, okay, that makes sense. Thank you.
Cool. No problem. All right. So here's a cool little trick. If your beta is a CH3, so in this case, like this beta here, it's a CH3. So let's say that I did this with a bulky base, like terpetoxide. What you're going to get is always a terminal alkene. Okay. So again, you just, if this is your alpha and this is your beta, you just erase the bromine. And between alpha beta, you just draw a double bond. Okay. Here's the arrows too for any of you that like to see the visual, right? That's what would happen. Okay. When your beta is a CH2 though, so when you have a CH2, so like the other example here, I'm gonna just move this down a little bit. So we have this here CH2. We still do make 2 products. So we do still take this H here, move this here like that. And then again, there is the alpha and the beta. So I can make my alpha beta double bond here. But there's usually 2 products because there's 2 hydrogens. So one product would be if I had this alkene here, which you guys can see is a trans alkene. The other product would be if I switched one side. So let's say I switch this hydrogen and this methyl and I make the cis alkene. Okay. Generally speaking, the trans alkene is the one that is more stable. So if you had to put a major product, it would be this one. Okay. But sometimes it won't be very clear what is cis or trans. So for example, let's say that I have, oh, there was that homework question. Let's see if I can remember what it looked like. I think it looked like this. Yeah. So it looks something like this. And so you use the small base like ethoxide. So when I label my alpha, I actually have 3 betas here. I have this beta, I have this beta, and this one here. But both of these chains are ethyl, so these betas are the same. So it doesn't really matter. Either one of these will work, right? So I'll just ignore the top one. But when I use a small base, CH3 versus CH2, right, I want to go with the CH2 because that's more substituted. So I will make the double bond that looks like this, but I will also, sorry, like that, but I will also make it if I switched one side. So let's say that I switch these 2 groups, right? I'll make this here, and this here. Okay, CH2s will always give you two products, right? When I look at these, it's not very obvious what's cis or trans, right? Because we don't use cis trans naming for trisubs, but we can talk about E and Z. So if you have a CH2 that you're reacting with and you make an E and Z isomer, right? The E isomer is typically the one that's better. Or, right, if I look on the left side, the bulky group is this guy and this guy here on the right side. If I just kind of track them again, right, I want the one where they're related in a trans way or in an E way, right? So this here would be the major product. Sorry, let me write major here. Okay. So little tricks you guys can use. If your beta is a CH, so for example, if this is your molecule here, you just draw what you see, really. I don't, someone tell me, did he ever use the term anti or anti-periplanar in class?
No, he
No.
didn't.
Okay, lucky
Yeah,
for
why
you
don't
guys.
they be taught us that?
No? Okay, well, I think I heard no. So luckily for you guys, it just makes it harder. It makes it harder if you know what that term means. But if you don't, then it's okay. It just means you just have one product, you just draw what you see. So you would get this here. Okay, cool. All right, so E2, you're making alpha beta double bond, and depending on the size of your base, which again, strong bases are what prefer this, right? You can choose for one side or the other. Okay, cool. So we'll call it on that for E2, just for the sake of time. Cool. So then the last mechanism is SN1E1. And the reason why we clump these together is because E1 is always going to be the minor product of SN1. They both follow everything the same. It's just the end result that differs. So what's going on with this reaction? Well, for this reaction, if I take my substrate and I just completely get rid of the nucleophile, let's say I just have solvent, right? Obviously, nothing is going to happen, right? So CH3Br, right? Only solvent, nothing happens. Okay. If I do secondary, right? Only solvent, nothing happens. But what's really, really interesting is that if I have solvent, but I have a tertiary structure, I start to see a little bit of product. Okay. So I see the solvent molecule typically adding, or I see some kind of elimination product. Okay. So, I mean, virtually the rate is 0, but here the rate becomes measurable, right? There is a rate here. Okay. So whatever is making this reaction fast, right, has to do with some intermediate that's stabilized by more carbons. Okay. Now, what kind of makes this, what makes this reaction even more apparent as to what the intermediate is let's say that I have a molecule that has 2 different tertiary centers, and I were to do this reaction with solvent. Not only do I get the addition of the nucleophile on that position where bromine is, but I also have some product where the nucleophile ends up next door. So the nucleophile rearranges. Well, if you think back, there was only one intermediate we've ever talked about that forms really well on tertiary substrates and also rearranges. SN1E1 is a carbocation intermediate mechanism. Okay. And it also explains why for methyl and primary and even for secondary, these guys don't react at all, because carbocation formation is only really good if you can form it on a tertiary center. Okay, so the way this mechanism would work is bromine leaves to form a carbocation, and then whatever is in solution, typically a solvent, right, will attack this this molecule. So a typical solvent is like an alcohol, or an alcohol can go ahead and attack. Okay, usually you'll get a protonated intermediate. Something in solution just picks up that proton, and what you get is, let me chart down here, something like this. So this would be our SN1 product. Okay, E1 would just look the same, or sorry, would follow majority of the same. It's just that at the end, what you get is an elimination. So that same alpha beta stuff, just now this time with the weaker base, okay, and with the carbocation. Okay, so for SN1E1, form your cation. Again, cations are a bit weird, right? They can rearrange. So it's always really interesting because with 8, you guys learn about alkenes first instead of the other way around. Usually in 118, they learn about these reactions first and then alkenes. So you guys have already been exposed to rearrangements. So those like canonical structures for rearrangement are also going to work here, just in the context of an alkyl halide. So for example, let's say that I had this alkene here. Oh, sorry, not alkene. This alkyl bromide here. Oh wait, actually, I guess I guess not. Because I just realized in your guys' class, you're saying that secondary is NR. So, I guess you wouldn't have to worry about this too much then. Okay, so we won't have to worry about that then. Because usually in other classes, we say that this still works. Right, and so you can experience a hydride shift, for example, on this. But I guess if you're saying that secondary cations can't form, then there's nothing to worry about here. You won't even see this happen anyways. So that's very good. That's one less thing to worry about. Someone raised their hand.
Yeah, I was wondering what the NR was.
No reaction.
Oh, okay. So those reactions after the solvent, there's no reactions.
Right. So these three, if you were to see either of these three, you wouldn't see a reaction at all. Like you would write in the box NR.
Okay, thank you.
Yeah. Good question. Cool. So I don't have to worry about that. So I'll put a star here, right? I really won't have to worry about rearrangement too much then. Okay. Now, generally SN1 is the major. So if you just have to put the major product, you can get away with just putting SN1. But I don't think you'll get in trouble if you put in the minor product for E1. Just remember that the E1 minor product is always most sub. So there's never a case where you can form a cation and you would make the less sub alkene from it. So for example, let's say that I form this cation here. If I had to choose one of these 3 carbons, I mean, 2 of these are the same, so I can ignore one of them. If I had to choose one of these 2 carbons, E1 is always the most sub. So you don't have to worry about bulky or small or anything like that. It's always the most sub. Okay. Cool. All right. So that should be good for SN1E1, just like a general overview of those reactions. And that's like a lot of material. So usually what you can do is you can organize all this like information into a chart, and that can tell you which reaction is more likely. One thing I'll tell you is that I would not recommend any of you like take a screenshot or, like just save whatever I draw now. What's really important about the chart is that you're able to make it and derive every single answer from it. Okay. Because if you can do that, then you won't have anything to worry about, right? You don't have to memorize a chart. You'll understand the material to the point where you understand why certain things will react a certain way they do. Okay. So the way that I make this chart is I put the substrates on the right side. So I put methyl. So actually, let's do it this way. CH3Br, primary, secondary, and then tertiary. And then I categorize the nucleophiles that we've talked about. So we've kind of talked about 3 of these nucleophiles we kind of talked about straight up, and then one of them was kind of like indirectly. The indirect one was we talked about weakly basic anions. Right, that was one that we talked about indirectly. But we talked about small bases. And we talked about bulky bases. Okay. And then we talked about solvents. So I'll put here solvents here. Okay, cool. So with this chart, all we have to do is look at substrate and then look at the nucleophile, and we can typically tell what reaction goes on. If I look at my weakly basic anions, I mentioned that these guys really love to do SN2. Remember, small bases love protons, just like these guys really love protons. So if I had to predict the reaction, they're mostly doing E2, but weakly basics hate protons. And if E2 is a proton mechanism, these guys are almost never doing any sort of E2. Okay, so for a majority of these reactions, I mean, especially for the methyl and the primary, we're going to see SN2. We'll see an SN2 for secondary. Just remember that there is inversion of chiral. Okay. And then for tertiary, SN2 is impossible. So weak bases, they have to substitute because that's all they're good at doing. So they'll do this by SN1, but it's super slow. Okay. Cool. Now, like we mentioned with the bases love protons. So they're going to love doing E2 because E2 was that proton mechanism. So for a majority of these, especially on these bulkier substrates where it gets faster, right? E2 is going to be the majority. It's going to be the major product. So secondary, tertiary, of course, he's going to do E2, right? I mean, this is where SN2 slowed down anyway. So, small bases are going to always have a lot of fun here. Okay. Where these two differ is that small bases will actually do SN2 on primary substrates, but bulky bases will continue to do E2. Okay. The reason for this is that sort of that transition state idea that we talked about, right? Was that if I have a transition state for a primary alkene, or sorry, for an alkene that's, for like a primary alkene, this transition state is not that stable because we only have one R group. So small bases are just not very happy doing this, right? Bulky bases, though, they're the exception. These guys, they are going to brute force an E2 if they have to. Okay, so these guys will do this reaction. They will do it. These guys won't, though. Okay, so bulky bases will eliminate primary, but small bases won't. Okay, and then again, like we talked about, you can't even do E2 on a methyl, so these guys are always SN2. Right, you can only substitute if you have to. Now, solvents are great because solvents do not react unless you can form a stable cation. So we only see an SN1E1 on the tertiary. Okay, and I don't want to say that this is super fast because I mean everything is relative, but compared to these guys, this is fast. So I'll just say this is fast, and in respect to the rest of these guys. Okay, cool. So we know what our substrates look like, and now we know what nucleophiles like to do what. Right, we should know what our nucleophiles look like. So here's just a general list of nucleophiles that tend to work. Weakly basic anions tend to be large. So when I'm thinking about those, I'm thinking about the halogens. So Cl minus, Br minus, I minus, those guys are large. Rs minus, so R can be anything, but sulfur is really good. That's a good one. A couple of oddballs, Cn minus is an oddball, N3 minus is an oddball. Okay. Actually, let me put large here, just to remind you guys, they're typically large atoms. Okay. Another oddball. So, okay, these guys are kind of like oddballs. Let me just mark them. So these ones you just have to like memorize probably. But if he's good, he'll probably just only ask from these first four. Okay. Those would be those guys there. Actually, I guess one little cool exception is that sulfur can also do this in its neutral state. So this is also like a cool little exception. So you don't actually need a charge for sulfur. What color is it? Yeah, this one here, right? You won't need that. Okay. So if you have things that are like below the first row there, so let me draw the periodic table here real quick. Cl, Br, I, PS, right? You'll notice that a majority of the people that we just talked about are like right here. They're below that first row there. These guys are really good weak bases. Okay. Now these guys up here, nitrogen and oxygen, and even carbon to some extent. So I'll include carbon. These guys are strong bases, and their anions are always going to be strongly basic. So I can put small bases here. Right. That's going to be your OH minus. You're going to be your NH2 minus or OR minus or R2N minus, right? Like the groups can be really anything. It doesn't matter. Carbon minus works too, but this is a really specific example. I wouldn't like worry about this one just quite yet. So I'll put a star next to it. Cool. Now the bulky bases, there's only two you need to know. I'll draw them out once again. Tert-butoxide and diisopropylamide. Okay, you can even just memorize these two. Not much need to know there. And then finally, our last category is our solvents. Okay, and there's two categories. There's like two basic ones for these. One is water, and the other is alcohol. So remember, you need only that thing on the arrow, and that's the reaction that's happening. Okay. I guess I forgot one thing. So if this is chiral, it produces both isomers. I forgot to mention that. So that's I mean, this is back to alkene kinetics, right? Or alkene reactions. Oh, thank you. This is just back to alkene reactions, where if you had a cation, right, the cation adds on either face, or the nucleophile adds on either face of the cation. So I'll just add that in. If it's chiral, it's both isomers that form on that center. Okay, cool. So again, I know that I wrote this chart out, and you guys can obviously take pictures or whatever, like save it and memorize it. But I think the best practice for tomorrow, right? The last thing you want to make sure you can do is you can sit down and you can tell me why every reaction happens in every column. And you can tell me why these nucleophiles are who they are, right? If you can do that, you can predict any reaction out there. You can do it with your eyes closed, right? Because all you need to really recognize is what kind of nucleophile am I using, and what kind of substrate am I using, right? That tends to narrow down quite a bit, right? Kind of saves you a lot of time. Okay, cool. So that actually took way longer than I thought it would. So let's just, so I'll have to clear this, unfortunately. Actually, I guess let's see, is it really that much in the way? Yeah, it really is. So I'm gonna have to clear this, but we can quickly do questions A, D, and E. So what am I looking for? So I guess you can, if you guys have the chart up, or if I know that Helix made one too, you can have that chart up. But what I'm looking at is the fact that this is a secondary halide, right? And this is an S minus. So if I think about sulfur, sulfur is a large atom, right? Sulfur is a large atom. So the anions of a large atom, right, that tends to be a weak base. So I'm thinking that this does SN2, right? All I have to do then is just confirm, right? Remember, SN2 works for primary, works for secondary, but tertiary is a no-go. So when I look here, this is secondary. This totally works. Let me actually put this in green. So primary is good, secondary is good, tertiary is a no-go, right? That's not going to work at all. But this is secondary, that works perfectly fine. Just remember, right, if it's secondary, invert if chiral, right? Invert if chiral. So I can draw practically all the same stuff, right? Sulfur is going to backside this wedge. So what's the back of the wedge? It's the dash. So we're going to have a dash bond here, and sulfur is going to add just like that. I'm sorry, CH2, CH3. Okay. Now look at the difference. Imagine if I use CH3, CH2, O minus, right? O minus is the first row or the second row? I guess I'll just call it the first row, but this is a first row anion. So it's small, right? And small atoms tend to be basic. Right, so this is going to be more likely, I mean, it can do SN2 or E2, right? But it's more likely to do E2, right? If it's primary, or I guess methyl and primary will do SN2, but if it's secondary or tertiary, it's going to do E2, right? When I look here, this is secondary. So we're definitely going to get an E2 reaction. Okay, so that means that if this carbon here were alpha, this would be beta, this would be beta. Right? These are differing betas, right? One's a CH3, one's a CH2. So if I have a small base, right, I'm going to prefer attack on the CH2. And so I will get an alpha beta double bond. So I can redraw the structure, right? This will be my alpha and beta. So I'll draw a double bond like that. Now, luckily, again, it's a CH2, so we'd make a cis and a trans. Oops, sorry, like that. But we want the trans one for major product, right? That's for the major products. So this is going to be major. Okay. If I wanted to attack on this beta, I'd have to take this guy and add some bulk to it, right? I'd have to add 2 arms to it. I'd have to make it tert butoxide or LDA, right? In that case, terminal, I mean, that's just terminal alkene. So I would get this if I used tert butoxide. Okay. So tert butoxide would give me that molecule there. Now, because this is secondary, sulfolysis or SN1E1 is just not going to work, right? Because we're not going to form a secondary cation. So lucky for us, if this were, let's say this were CH3, CH2, OH only. So let's see. So let's say that it was, so what would that look like, right? It would look like this, and it said like CH3OH, right? So it's a solvent molecule. It is not a weakly basic anion. It's not a strongly basic anion. It's not a bulky base. It's just a solvent. This would be NR, no reaction at all. Okay, cool. So that's that one there. So go ahead and save that. Let's go look at the other two. So D, I mean, I think I already know what this reaction is because I see this guy. I see terpetoxide. And terpetoxide, we talked about this, right? Terpetoxide is a bulky base. And unless you're methyl, right, which will do SN2, bulky bases on every single other substrate are doing E2. So when I look at the center here, I'm not even batting an eye, right? I instantly know what this is. It's secondary, right? So I know this is an E2. Now, luckily, you know, Dr. Helix blocked off this beta carbon here, so there's no hydrogens. So I actually don't even have to worry about this guy here. So alpha, beta, right? There's two betas, but this beta has no hydrogens. So I don't have to care. So I don't care about it. Okay, I don't care about it. So I only have to worry about that one. So I just got to make the same structure, but between this alpha beta, just make a double bond. Okay. Hey, let's say that it was there. Let's say that it was open, right? Let's say that it was open. Then, I mean, it would not that it makes a big deal. It's still a CH2. So we would still get this alkene here. But if I were to do this with a smaller base, like let's say that I cut off these arms here, made it an ethoxide, then I would get my alkene over here. Okay, so this would be, so this is my terpetoxide answer, right? If I had gotten rid of that bulk there, and this would be my like ethoxide answer, right? Smaller base answer is what I would have gotten there. Again, there's also a cis answer too, right? But trans is the one that we want, right? We want the more stable of the two. Okay, cool. Now let's say that I had, let's say that oxygen leveled up. Let's say that it evolved into a sulfur. So let's say that I had ethoxide, or sorry, sulfoxide, or ethane I don't know, whatever you would call that. You would call it something. I don't remember what though. But let's say that we had a sulfur here instead, right? Well, hey, sulfur is a large atom. The anion of a large atom is a weak base, right? I'm going to see SN2 here, despite all the bulkiness, right? We'll get a slow SN2, right? That SN2, this is a wedge face. So the backside is the dash face. So sulfur will add in at the back here. Okay. Let's say that the iodine was a dash, right? And what I used was NaBr, right? Again, the anion of a large atom is a weak base. So I'm still predicting SN2 here. Right, secondary, but now my backside is my front side, right? Because hey, dash, what's the back of a dash? It's the wedge. So this is going to be a wedge like that. Okay, cool. All right, so let's just do the last one, and then I've got to call it, unfortunately. Tertiary substrate. Okay. So tertiary substrates, one thing to think is that there's only two reactions that can happen here when we look at the chart, right? We can either get an SN1 or we can get an E2, right? So if I have an anion, right, that anion is going to do E2. If I have, a basic anion, right, that's going to do E2. If I have a solvent, or I guess if I have a weakly basic anion as well, right, it would do SN1. Right. Yeah, let's make that distinction, right? A strongly basic anion will do E2, and then a solvent or a weak base will do SN1. Well, hey, I don't see an anion at all. It's only a solvent molecule. It's got to be an SN1. Okay. So all I'm going to do here is replace the bromide. Oops, sorry, CH3. Select that. Now, to make this a little more interesting, right? Let's say that it was actually let's say that we had I'll just put R here, and I'll make this a wedge, and I'll make this a dash. Let's say I had this bromide, right? And I did the reaction with this bromide, right? So I'm forcing it to be chiral, right? What's going to happen, right? I'm going to have two answers here. I'm going to have one answer where the methoxy, or the methanol replaces exactly the same. Oops, that should just be R. And then one where it inverts. Okay, because remember, if I have a chiral center, then I'll produce both isomers because we're going through a carbocation intermediate in SN1. Okay. A couple people asked me, is it okay to draw the E1? Of course, right? That's not a big deal. You could draw the E1 if you want to, but it's not a major product, it's minor. So you don't really have to. You can get away with not doing that. Okay, cool. All right, well, with that being said, I have to call it there. So it's so unfortunate. There's so much more stuff we could have talked about, but it's okay. Cool. All right. So usually these take a couple hours to be done. So it should be done in like an hour or two. If I don't put it up by like 9 or 10,